In the previous episode of this three-part series, examining electric plasma discharge, I described a typical plasma discharge as it would be generated in a research lab. So now, as we progress into part 2, we'll compare the volt-ampere characteristic that we developed for that lab plasma with what astronomers have told us about the sun's atmosphere. And perhaps the single most important fact we learned in that first episode was that wherever the volt-ampere plot in this figure has a negative slope, that is to say, such as from points D to G and from H to J, and when it goes from the upper left to the lower right, that's a negative slope. When that happens, the plasma will try to form itself into filaments. So one thing we should keep a lookout for now is anywhere in the solar plasma that it forms filaments. But how can we make that comparison between a lab and the real thing when the sun is a single sphere sitting out there in space and not in a cylindrical tube in a plasma lab? Well, the cross-sectional area of any cylindrical tube typically used to study plasma discharges in a lab is the same size at all points along its length. These circular cross-sections are kind of like salami slices cut through a cylindrical-shaped sausage. They all have the same area, and therefore, with a constant current flowing along the tube, the current density in amperes per square meter is the same at every cross-section along the length of the plasma because they all have the same area. But when we consider the real sun, a spherical geometry exists, and we have a spherically shaped plasma with the anode sun sitting at its center. The cross-sections through which the current flows in this plasma constitute a set of imaginary, let's say virtual, concentric spherical surfaces, or shells, not a set of circular slices taken through a cylinder. Imagine one of these virtual thin spherical surfaces that has a very large radius. The fixed amount of our sun's total current passes through it, just as it does through every one of the other concentric spheres. But since the surface area of this imaginary spherical cross-section is so large, the total current results in only a very few amps flowing through each square meter of that surface because there's so many square meters. The value of the current density, in other words, in amperes per square meter is low, way out there. Therefore, we're in the dark current mode. See the left side of the figure. The plasma doesn't glow, and we have nothing to tell us that we're in a plasma discharge at all, except possibly some radio frequency emissions. We are also in the extreme left section of the first figure. Moving inward from deep space toward the sun is equivalent to moving from left to right in both these figures. As we get closer to the sun, the imaginary spheres have ever smaller surface areas, of course. Therefore, the value of the current density continues to increase, and we eventually enter the normal glow region of the plasma. This is what we call the sun's corona. The characteristics of the radiated light are much like those of a neon sign. As we approach still closer to the sun, the spherical surface gets to be only slightly larger than the sun itself. The value of the current density becomes extremely high, and we enter the arc mode region of the plasma. This is the photosphere, the brilliant region of anode arc mode tufts that most people inaccurately call the surface of the sun. But the characteristics of the radiated light here are much like those of an electric arc welding machine. Intense ultraviolet light, strong radio frequency noise. Now at that point, consider what would happen if the sun's diameter increased very slightly abruptly. Assuming the total current remains a fixed quantity, the sun's surface could lie entirely outside the arc mode boundary right there. If that happened, no plasma tufts would form, leaving the sun's size unchanged and decreasing the total current would also reduce the current density at the sun's surface and produce the same effect. In either case, such a sun would not have a photosphere. Now, this demonstrates why we can say that a photosphere, that is to say a plasma arc mode tufting layer, covers any star that's too small relative to the intensity of the electric current impinging on its surface. Ralph Jurgens, in his original Electric Sun paper, describes the trade-offs between the size of a star's surface area in comparison to the strength of the electric current passing through it. Hey, let's perform a thought experiment, a Gedanken experiment, as Einstein would say. Let's take a virtual journey out from the sun, knowing what we know now. Having made the imaginary journey from deep space in toward the sun that we did in this part 1 of this video, let's now reverse the trip and think about what we might experience going back outward from the photosphere, all the while keeping in mind what both of the figures that we just developed now tell us about the electrical surface and electrical structure of the sun's plasma surroundings. We'll cover the same distance we did before, except in the reverse direction. So what should we expect, given what we have gleaned from those two figures? We'll start off just below the visible top level of the sun's photosphere. This is at the far right-hand side of both figures, where the plasma is in its smooth, that is to say, non-filamented region of the arc mode between points K and J. We can't see into this region from outside the sun because the brilliant opaqueness of the arc mode begins out at point I. As we move to the left, up from the sun's interior, out to a point between points J and I, we might expect to see evidence of the forming of filaments because the E-field plot has negative slope there, as we just discussed. But of course, we can't see anything in this region of the sun because of what we just said about the entire region being opaque. If it's opaque, you can't see through it. And in the SAPHIR experimental chamber, however, we can see the formation of groupings of like charge, even though we can't see it on the real sun itself. These groupings are the beginnings of filamentation, the gathering together of like charges in order to maximize the value of the current density and thereby minimize the electric force each positive ion experiences. Many images of the actual photosphere are available that show the tops of these filaments just at the limit of our ability to see them because closer in the sun is opaque. Anyway, this is an example of the one-to-one match between the properties of the plasma discharge in the SAPHIR lab and the actual observations of our sun. This series of images was obtained by the SAPHIR team. It shows how filaments begin to form on the surface of the anode in the low current density region of the arc mode, that's points J to I. Point I corresponds to the top of the photosphere where such cells are visible. Classical astronomers talk about seeing granules on the surface of the sun, or they talk about the tops of convection columns when they see these tops of these filament plasma tufts on the photosphere. This figure shows how filaments grow in number and density as the value of the current density increases from left to right in the figure. The large center image shows how multiple concentric double layers of charge can surround the sun. The image on the far right in this figure shows the beginnings of the formation of a corona structure, and that corresponds to the H to G range in our figure. But before we think about leaving the upper photosphere at point I and entering the lower corona at point H, we ought to note that this is one of the most important regions on the sun. The transition layer, sometimes called the chromosphere, the arc mode to glow mode transition, and for us it's points I to H, is the location of a major double layer that contains the largest voltage drop, the strongest electric field on the sun. Anyway, take a look at the glow to arc transition I to H on the figure. Over a relatively short radial distance, going in the direction that outward direction we're going, the E field strength increases quite abruptly. This has two effects. One, the outward force of ejection on the plus ions gets much stronger. That's what the electric force is. It's a force on positive ions. And two, the slope of the voltage in volts per meter gets much steeper downward. Remember, the E field is the negative of the slope of the voltage plot. So this next figure presents some of the data SAPHIR collected in this region. This is one of the most important results that I think SAPHIR came up with. The presence of the double layer is shown by the thin black curve at the bottom of the plot, and it's labeled charge density. The horizontal axis shows our radial distance r out from the center of the sun. In this plot, the radius r is increasing from left to right, whereas the two earlier figures showed r increasing from right to left. Please take note of the following phenomena exhibited in this SAPHIR plot. Number one, the value of the charge density is shown in black. The green plot shows the strength of the E field outward force on each positive ion. The maximum of the E field plot in green occurs at point D. The maximum downward slope of the red voltage potential energy plot is right there. This is analogous to a ball rolling down a hill due to the gravitational force on it. In our case, the force is electrical, not gravitational, and this obeys Maxwell's equations rather than Newton's. And Maxwell's equation is that the E field is the negative of the gradient of the voltage. Or in other words, in English, the E field is the negative of the value of the slope of the plot of the voltage plot. So this radius value, the positive maximum of the E field plot, is the location where the downward slope of the voltage plot is steepest. See the red curve, you can see it's steeper there. Therefore, it's also the location where maximum outward force toward the right in this figure is applied to each positive ion. Thirdly, this large voltage drop in red is exactly what the electric sun model predicts should occur. Fourth thing is SAFIRE's experimentally obtained measured value of 8,000 volts per meter disproves the bogus claim that astronomers sometimes make that plasmas cannot support electric fields. Yes, we measured it at 8,000 volts per meter. A positively charged spherical layer is located at radius point C. Its location corresponds exactly to the steepest rise in the E field plot. Let me say that again. The positively charged spherical layer located at point C is at exactly the right spot. Its location corresponds exactly to the steepest rise in the electric field, the green plot. Sixth, a negatively charged spherical layer is located just to the right of point D. Its location and thickness from radius values D to E, you can see it's a little thicker than the positive one. This corresponds to the location and radial extent, the thickness of the downward pitch of the E field plot. You see the green stops at point E, stops going down. These two concentric spherical layers, the positive and the negative, constitute the double layer predicted by Ralph Jurgens and other investigators of the electric sun hypothesis. All the observations listed above can be considered tests that the electric sun hypothesis passed successfully. In other words, had these results not happened, had SAFIRE not come up with this curve, it would have strongly suggested failure of the electric sun hypothesis. Thank goodness that didn't happen. This came out completely confirming what Jurgens had originally proposed. The two unmarked peaks in the green E field plot at radial distances 12 and 15 indicate the presence of additional but much weaker spherical double layers. The fluctuations at point A and B in this figure are due to the way positive ions are formed inside the SAFIRE chamber. In the actual solar atmosphere, positive ions are simply ejected. You can think of it yourself. From deep within the sun, within the photosphere, they float up into the plasma in the lab because they can't travel in wires. Positive ions do not come into the plasma from the anode because they can't come through the wires into the anode. They have to be generated in an ionization process, which does not occur in the case of the real sun. This is the single only major difference between the lab experiment and the actual solar plasma. These SAFIRE results are in complete compliance with Maxwell's equations. The principal quantities that SAFIRE measured are the electric field strength, E in volts per meter. Also, that's the force per unit charge. They measured the charge density in coulombs per cubic meter, and they measured the voltage V in volts. You can see those quantities plotted there. The cause-effect fundamental relationship amongst these quantities, all of them have been well known and long accepted in electrical plasma engineering science. They are historically defined in great detail by the canonical Maxwell Heaviside equations. Wherever possible, SAFIRE's measured interconnected variations in these variables were checked using the appropriate Maxwell equations, and they were consistent in every instance in which we checked them. This next picture is a sun's corona as seen during a solar eclipse. Several so-called coronal caps, regions of converging plasma streams leaving the sun. You expect plasma streams to diverge, but these caps are where they actually converge for a bit. And you can see it there in this beautiful picture of the eclipse. So now that we are in the lower corona, points H to G, the lower corona is a smooth, non-filamented plasma. Notice no more filaments. In the image, the relative smoothness of the continuous plasma just above the bottom of the corona You should notice that. It's important. This is consistent with the positive slope of the electric field plot over this range of radius values, saying, no filaments here. In this image, some of the reddish chromosphere plasma is just visible above the edge of the moon's eclipsing disk. This is the region where a maximum turbulence and thus maximum temperature is produced by the positive ions that exit the acceleration of the double layer when they collide and mix with densely packed, unfilamented other ions and neutrals. This brings us to the outer or upper corona. That's points G to F. Now, if you notice point G to F, the farther out we travel in the corona, the more filamented the discharge becomes. Note that the coronal caps, regions where the outward streaming plasma is beginning to converge to form filaments, they occur within a plus or minus 55 degrees latitude range, typically either side of the sun's equator. And they call this the streamer belt, where these streamers form, or this filamentation process is what it is. Clearly predicted by the negative slope of the electric field plot in this range, again demonstrates the correspondence between the SAPPHIRE data and the actual behavior of the sun's surrounding plasma atmosphere. Outside the streamer belt range, nearer the sun's poles, the plasma is in the form of laminar, closely spaced but diverging filaments. It's quite possible, I think likely, that electric current is entering the sun in these polar regions in what are called polar crown prominences. In these figures, we're seeing plasma. We're not seeing the sun's magnetic field or its electric or gravitational fields or anything else. In these visible flows, we are viewing glow mode plasma, visible plasma, and it's generally following both the magnetic and electric fields, but those fields are, of course, invisible. It's only the plasma that we see. Don't forget that. There's a definite need for increased study of these polar regions of the sun, in my opinion. Is the direction of net current flow in these areas inward toward the sun, or is it outward? Does the current have a helical structure like a Birkeland current, or is it a bunch of BCs being squeezed together? It's difficult for NASA to position a probe into locations from which good polar observations can be obtained. At present, we can only watch, wait, and hope that NASA takes an increased interest in the sun's polar regions. Next figure shows how coronal caps converge into outwardly directed streamers. This is the range G to F. Now, in the volt-ampere plot, this is a range where it has negative slope. So it's predicting the occurrence of filamentation. Birkeland currents. Some of these streamer filaments may travel out to the various planets. It's likely that the strongest of them are indeed the Birkeland currents that eventually end at the poles of Jupiter, Saturn, and Earth, planets that exhibit strong auroras. The most distant extent of those Birkeland currents determines, or is determined by, the boundary between the glow mode and the dark mode of the sun's plasma atmosphere. That's at point F. In the next episode, we'll conclude this three-part series with a hard look of what and what not to realistically expect from the Parker Solar Probe, a descriptive ride of the journey the solar wind takes to the heliopause and the outer boundary of our solar system. And finally, how we've been able to witness the transmutation of elements in the lab on Earth, which just might be an accurate recreation of exactly what is happening on the sun. Our mission continues to showcase the facts and evidence to validate that indeed our sun is electric.